Alrighty, hey guys, my name is Jack, and I'm super excited to share with you guys this project that I've been working on for about the last month. For the last 2 weeks, or the first 2 weeks of uni, I've kind of just been ignoring all my extra commitments and all my uni work to try and get this guy done for Hardware Flex. It's a lot more work than I expected. So what is it? It's an analog robot that's solar powered, and basically it just tracks the light. So at the moment, it's trying to track the window over there, but if I give you a little demonstration with this flashlight, and moving around to track the light. And it's all free-formed, all analog circuitry, so there's no microcontrollers. All of the logic is purely analog, and you can see, if I try and get it to face over this way for a second, you can see all of the circuitry here is all free-formed. I think there's about 2 meters of brass wire back there. So the only other thing it does is that if you give it a couple of whistles, it'll do a little dance for you. I've had to wait a second to show this off to you because when that red light there is on, that indicates that the dancing circuit has been locked out. The last thing I want to show off is that I have this bell jar for him, but I don't think it comes out as well on camera, so I left it out for the beginning of this video. So why even build analog robots? Well, I built a couple of these analog solar powered circuits, and they all originate from this old electronics movement called beam electronics, which it was popular in the late 90s to early 2000s, if I'm not mistaken. And these beam roboticists were trying to imitate nature with the technology they had at the time. But very quickly fell out of fashion with the advent of microcontrollers. And you can probably see why when you look at the circuit. There is a lot to the circuit and it doesn't do very much. And in fact, I reckon this robot can be programmed in very, very few lines of code. But I also feel, and maybe this is getting a little too philosophical, but I feel like this robot has so much more personality and so much more life than even really complicated artificial intelligence. And I think you lose something when you digitize that logic. There's something much more lifelike about it being analog. And I have some book recommendations, I can go into it more, but not in 8 minutes, so I'll just move on. Mostly, though, I am building these circuits for the art of it. I think there is something beautiful about a freeform circuit, and the functionality is secondary to that, and it just kind of adds to the art. So I treat these more like sculptures than as a functional piece of hardware. Alright, we're going to try one last time because I keep going way over time with my circuit explanation. You might be able to hear one of my other solar circuits going on in the background. That is the solar marble machine. In any case, there it is. I've taken the circuit off the base and disconnected the motors so you can see more detailed the freeforming. And this is the circuit diagram. It's just hand-drawn because I didn't have time to put it into a proper program. Pretty much we can split the circuit into 3 main sections: the charging, the motor controller, and the microphone circuit. The charging starts with the solar panel. In fact, everything starts with a solar panel because I kind of wanted this circuit to work well indoors and all day. And that's only possible thanks to these super efficient monocrystalline panels from DigiKey. They claim to be 25% efficient, and the real kicker is that they work well indoors, which most mono and polycrystalline cells tend to struggle with. Also a little bit expensive. I think that one was like $40 for the larger one. You can split the panel by cutting a trace at the back, and that allows me to use some simple logic to either run the panels in parallel or in series, which in essence creates a really, really rudimentary maximum power point tracking circuit. That maximum power point tracking circuit is here on the actual freeforming, and you can see that when the threshold voltages are reached and the panels start operating in series, this amber LED turns on. You'll notice that all of the LEDs on this model are really dim, and that's because obviously there's not much extra power to play with to run LEDs. So all of the LEDs are run through 100K current limiting resistors, which means they're only operating on about 20 to 30 microamps. And the only reason we can see them kind of clearly is because they're super high efficiency LEDs. It actually looks kind of cool at night. They're very, they glow more than turn on. It's weird. Anyway, the solar panel then, in fact, there is one LED that turns fully on. I should probably mention this. This is my overvoltage protection circuit, which just connects directly to the solar panel. It's awful, and to be honest, I'm kind of embarrassed to even show it off, but I needed to design something quickly because I kind of forgot to design it. And it actually works really well. It turns on really sharply within like 100 millivolts, which is what I need, so it turns on sharply so I don't waste a lot of energy. It's very dependent on component values. You can see there, I have 1 to 10K for that resistor value to tune the circuit to operate properly. So don't look at that too much. In any case, the solar panel then charges these 2 storage capacitors, and we have, in the beam world, we call this a solar engine. which pretty much just once a threshold voltage is reached, at 3.5 volts in this case, it turns on the rest of the circuit. And when a lower threshold voltage is reached, 2.5 volts in this case, the circuit shuts off. By default, I'm charging this small 330 millifarad capacitor in here. That then runs the rest of the circuit once 3.5 volts is reached. But also, once 3.5 volts is reached, we start charging the 7.5 farad capacitor. That is the larger storage capacitor, which you can see here. What that does is that it means that when it's very early in the day, the bot can use the 330 millifarad capacitor charge to turn and face the light. Once it is locked on, start charging the 7.5 farad capacitor, and then that is the larger one that charges. And once the 7.5 farad capacitor charges high enough to match the 330 millifarad capacitor, we're essentially operating on the 7.5 farad capacitor now. It works all right. I thought it was a quite elegant solution to that problem. Yeah, the next part is the motor control, or the sun tracking. Again, I think it's a really elegant circuit, but I don't have too much time to go into it. The way I would describe it for electrical engineering students is it's pretty much just a P controller with a massive deadband. So ignoring that part, all we have is a CMOS oscillator whose duty cycle can be influenced by this photodiode bridge. If we ignore that and then we ran those straight into these other inverters, that would just be a reversible motor controller. Adding in the low pass filter creates that massive deadband. And I also have these two micro switches on the up-down motor, which will just hold one of the inverters low or high so that the motor can't overshoot. Finally, we have the microphone circuit. Again, I think it's really interesting, but I don't have too much time to go into it. We have a preamplifier, which then goes into the actual logic. This first part just makes sure that the pulse lengths are long enough and that the time between pulses are short enough. Sorry, are also long enough, yes. So that random sounds don't trigger it. It actually has to be like 3 proper length whistles. The next part is a charge pump, which charges up this 330 microfarad capacitor. So 3 pumps, and it trips this circuit, which then discharges the 330 microfarad slowly through the 1 mega ohm resistor and turns on the next part, which is a dance enable circuit, which enables the final oscillator. But it also activates this monostable oscillator, which then holds the whole circuit low, or holds the whole circuit off until it reaches its time constant, which in this case is about 20 minutes. It's a really long time constant. Finally, we have 3 oscillators, which just bias the motor controllers to make them oscillate, and then 1 for the flashing circuit. And if we look at the actual freeform circuit here, that is the maximum power point tracking circuit, the over voltage protection, the 2 capacitors, the solar engine. These 2 here are the motor controllers, and this here is the preamp, the microphone logic, and the final oscillator.